And welcome back, ladies and gentlemen. Today we are going to start our introduction to the LC3, but we're going to start first with a review of what we've learned. So let's jump in here to an introduction into the world of computing. And if you recall, or you may already know, and you've probably already kind of guessed at this, but computers are not electronic geniuses. As we've done work with all these logic gates and everything like that, you might have noticed that there's a lot of steps that go into determining everything. And our approach so far has kind of been to build from the bottom up. Notice we started first in this course to talk about things like binary and hexadecimal, then we moved to logic gates. And so there's this whole process of us going from starting off talking about bits, then talking about gates, and then lastly we're going to be talking like things like processors and instructions. So we're just kind of gradually building everything up to kind of like learn more and more of these different things that are going to be going on in the world of computers. So some reoccurring themes that occur, and they're not just necessarily in this class, but in computing in general, all right, are abstraction. Pretty much what this means is there's not a need necessarily to worry about the details, all the fine stuff, until something goes wrong. Generally speaking, you're going to be looking at the larger, overscoping picture, and you'll hammer out those fine details when you get to it. But generally speaking, you're going to kind of plan out generally and very broad. The importance instead is placed on how these different components are going to work together. For example, in software development, when you start approaching how to tackle something, you look at it from broad strokes first. You're like, okay, I know I need to have a loop here. I need to have like a prompt here for the user in order to gather input. You're not going to sit there and start figuring out, okay, what do I need the program to say to the user? What variables do I need to have named? You're not going to worry about that stuff right away because at first you're going to kind of approach it from broad strokes. And this is the same for hardware and software. Both are components of a computer system. You can't have hardware without software and software without hardware. If you have hardware that does not have software, you pretty much have a giant fancy paperweight. If you have software but you have no hardware to run it on, you kind of just have this useless piece of program sitting out there that has no purpose. And here's the thing, there are pretty much two specialty fields out there. There's people who delve into, go into computer engineers are more about the hardware side and developing things there. And then the software side, more computer scientists who deal with development of programs and applications. So despite these two fields, even if one person specializes in one field or the other, they really should have a good fundamental understanding of the capabilities and limitations of both, because as a software developer, which is more my background where it comes from, I should know the physical limitations of hardware. I can't just say, well, I'm going to use every last little bit of RAM out there in memory so that way I can have this program just load everything, it'll run super fast. But then you have to consider, well, what about the device that you're running that on? What's if that device doesn't have as much memory? Or what's if what you're wanting to do has more memory needs than what most of your market you're targeting is for? These are all things to consider. No matter if you're a hardware developer or a software developer. Hardware developer could make some really powerful hardware, but unless there's software that's going to utilize it, it's more theoretical and not an actual application. All right, now let's skip from theory here and let's start applying that into practice. So how do people take this stuff in theory and start putting it into practice? So in theory, this is theory, a computer can compute anything that's possible to compute, given enough memory and time. Remember I said one of the big things before I said, I'm going to load everything up in memory, go super fast, and but you might run out of memory. So you got to make sure you have enough memory to be able to do this task. All right. Another thing is time. It takes time to develop a program. It takes time to debug a program. It takes time to have the resources available for that program. Like for example, people that might look at video games, it takes time to make all those different assets you're going to be using for that video game, whether it's the audio, whether it's the character models, whether it is rendering different environments. All that stuff takes time. In practice, all this stuff, time, cost, power, they invoke problems that we saw first. So if I'm looking at time, well, obviously that's a pretty self-explanatory. Cost is a huge thing. Any of the stuff that goes into making these kind of applications usually involves a lot of man hours. And while you have to pay these developers in order to make things, so that is going to incur cost. Plus, if you have to write licenses for anything, whether it's like, let's say, an engine license, Well, you're going to have to pay for that if you're developing video games. If you want to use Unity 4, if you're selling more than so many licenses, you're going to have to pay for those costs. And power, what does it take for this application to run? Does it have a very large power draw? Can it run on low power machines? Because that could make a difference on what kind of devices you're able to put this on. So let's talk then about the fundamental flow for computers. When we're examining these layers of abstraction that are used, it kind of forms a systematic sequence that gets developed. And the first thing is the problem to the algorithm. Right? And this affects software design. So you have to choose an algorithm and data structures. And what a problem pretty much means is, okay, I know that I want to go and I'm going to make a very basic example here without getting into anything too complex. Let's just say I want to be able to build a basic calculator that just does addition, subtraction, multiplication, division. Nothing too complicated. Right? It's a very basic calculator. Right? And so, well, if I run that calculator, I don't want to just run once. I want to be able to reuse it without having to relaunch the application. So that's a problem that could occur. If I just have the program run once, do as a calculation, but then the application doesn't do anything, well, that's a problem that I'm going to solve. I'm going to have to develop an algorithm. I'm going to have some kind of loop that takes that program when the person does it and starts it back at the clear screen. When they press clear, it wipes the program, starts it over. Those sorts of things. All right. Now that algorithm then turns around to develop into the program. So you say, hey, I know I need a loop. What kind of program do I want to do? So you start looking at programming. So what languages are you using to express the design? Are you going to write it in, for example, an object-oriented programming language such as C++ or Java or C#? What are you going to be doing that's going to do that? Because each programming language has its strengths and has its weaknesses over each other. Some are a lot easier to learn from the development. Some are more powerful. But there are trade-offs with each one. Then the program is in turn going to affect the instructional set architecture, or ISA as you might hear it called sometimes. This then is the compiling and interpreting side. So how it takes the stuff that you've written and convert it from a text language that we're used to seeing into machine instructions. So remember, machine instructions, things like the zeros and ones that the machine can actually interpret. But let's go a step deeper. Let's go just a little bit deeper and examine the flow. So we would just talk about the ISA, but from there it goes to the microarch, and this is the processor design. This is choosing structures that implement it. So now you write this program, what kind of things are actually capable of this? Because the kind of computing that goes on in, for example, a smartphone is going to be very different from the kind of computing capabilities that are in a high-end gaming PC. Yeah, they might have similar architectural designs. Like they might even both be, let's say, running Windows. But you're going to have different things that are going to be in there besides just, let's say, your CPU. You could have different memories that you have to worry about. You have different things within the GPU that you can worry about. The one may not even have a dedicated GPU. It might be integrated. These are all things you have to look at when you're looking at these design processes. For the microarch, you start looking then at circuits. All right, so this is now getting down to the actual construction of that machine. So this is now a little bit more towards the hardware side of things, less of the software side. Software developers usually don't start getting into this much control, but the hardware developers are. So the people that are thinking of things like making video cards, they really start examining stuff to figure out how can we handle this information that's coming through and make it more efficiently handled. All right, and this is when we start getting into things like logic and circuit design. Remember, we talked about logic gates. All right, so those gates and low-level circuits are things that they use to implement these different components. And we're not going to talk too much about low-level circuits. We'll talk a little bit more about that if you take computers inside and out, which is my complementary class for next semester. We'll talk a little bit more about the hardware side. Here we're delving a little bit more on the software side. But this again is the next level. From there, from circuits, we start looking then at the actual devices, right? And when we're talking about devices, this really gets into the process engineering and fabrication. So what do they have to develop and manufacture for the lowest level components? What kind of chips need to be manufactured? Are we looking at getting like the newest and greatest Intel chip? Are we looking at getting, maybe AMD? Are we looking at some kind of third party? What are we going to be putting in here that's going to support the architecture, it's going to support the design for everything that we need for this demand. This is all part of that process that goes into making a computer and also into anything for even software development, because software development has to know what is the capabilities of the machine that you're running it on. All right, enough of that though. Let's do a little recall here and go back to representing data. So recall that at its lowest level, a computer is an electronic machine. It just is. It's not analog, it's electronic. And typically we have talked about that there's two states: a presence of voltage, which we represent with using 1, and absence voltage, which we represent using 0. This binary representation of this basic unit, of course, if you remember, it was a bit. So 0 and 1 were bits. Right? And of course you had 8 bits that made a byte, so on and so forth. This is all information we've already talked about. But we want to kind of start thinking about this as we're moving into this chapter on the LC3, because it's going to really help us when we start talking about using binary for programs, using hexadecimal for programs, and using even some assembler. Now, values, of course, if you recall, they have more than 2 states. So rather anything more than just 0, 1, are going to call multiple bits. So even if you're like, I'm looking at 4 states, I now have 0, 0, 0, 1, 1, 0, or 1, 1. And that's just to do 4 states. And of course, if you want to do anything more than that, it's going to grow pretty quickly. Now, what a computer needs to represent, all right, these are the different things. Numbers, obviously, a computer has to be able to represent numbers. And this is signed numbers, unsigned numbers, integer, floating point, which, for the normal people who think that's like your decimal numbers, the numbers that have a decimal point is, so like 2.5 would be considered a floating point number. Complex numbers, rational, irrational. So sorry, getting into things like pi, things like I, E, anything like that that might be in here. Fractions. The computer has to know how to be able to handle all that stuff. It has to obviously be able to handle text. Think about even your thing that you probably carry around every day, your smartphone. You're not just putting numbers in to send messages. You're sitting there and you're typing out a message and you're doing it via text, because not everybody's going to know how to convert every single text character into a binary string. Right. Next up, images. Right. This includes pixels, colors, and shapes. Right. An image is, at the end of the day, a series of bits that the computer interprets to be able to make the image that you're looking at on your screen. And of course, you have sound, pretty self-explanatory. You have logical, which includes true-false operations. And lastly, instructions. So that would be things like, for example, programs. What do you want the computer to do when you click a key on the keyboard, when you press a button on your mouse, when you touch your screen? What is that computer doing? All right, let's do a quick recall on what unsigned and signed integers mean. All right, unsigned bits, if you recall, are usually from 0 to 255. All right, and this is looking at an 8-bit string. All right, if you do more than that, obviously, if you have a 16-bit string, you can have more than 255. But we mostly talked about 8-bit when we look at the LC3. We're going to be dealing with 16-bit, so we can actually go a lot higher than 255. But we'll deal with that as we come to it. All right, signed bits, of course, if you remember, for 8 bits, is from negative 127 to 127. All right, a little refresh on binary operations. We've discussed binary operations such as addition, subtraction. We also did a little bit of work with multiplication, division. Remember, the biggest thing is with the subtraction, you got to worry about, if you're doing like one complement or anything like that. But when we start dealing with programming with binary, an important thing to remember is that the sum or difference must be represented with the same number of bits. So if you start with 8-bit addition, your final number should be an 8-bit. You say, well, I know when we did some binary addition, sometimes we ended up with 9-bit numbers. Or if we did, something crazy, it's like, hey, it's a 9-bit addition. What does that mean? Did they put down all 9 bits? Yes, it does. When we're dealing with binary addition, we were just practicing it. It's 9 bits. However, if the operands are too big, if you end up with something that the answer actually cannot be represented in a computer like that, you won't get a 9th bit just magically added on. The computer doesn't do that. Instead, you get something called overflow. And this often occurs when the signs of both operands is the same and the answer is a different sign. So usually you'll see a lot, especially in signed integer notation. It happens pretty frequently. Even in unsigned, it can happen. And what will happen is it goes beyond the signed bits that are allowed. So when we start looking at, for example, let's say we have an 8-bit unsigned and I have 1 plus 1 in that 8th digit, suddenly that would now have to go to 1, 0. But if it goes to 1, 0, now we have 9 bits. And that's an example of an overflow. And what would happen is that it would actually misrepresent the number that we should have. All right, some logical operations, and or not. All right, and of course is useful for clearing bits. And when we start dealing with the LC3, this is a lot of times we're going to use the and for. All right, and with a 0, of course, it just represents 0, and with a 1 is no change. So if you look here on this example for the and, you can see that what I'm doing is I'm clearing those bits out. 1, 1, it makes it 1. But then from there, also, if you just keep kind of going through those, you'll notice that we are applying an and operation. We're making it so that way it's an and operation. So if you have 1, 0, that's 0. If you have 1, 0, that's a 0. 0, 0, that's a 0. Because remember, unless it's 1, 1, like you see here in 2 of those bits, it's a 1. That's the only time. Both of those bits have to be true or a 1 in order for us to have a 1. Because you notice all the rest of them are zeros, because even though there might be a 1 there or 0, we're not adding. Because if we were adding this, we'd have something totally different. But here, because we're anding, you end up with the string 0, 0, 0, 0, 0, 1, 0, 1. Similarly, when we look at OR, this is used for setting bits. All right, so you want to set the value of a bits. So again, OR with a 0 is no change. OR with a 1 is a 1. Right? We know this from our logic gates that if there's any kind of 1 in there, then that means that that's going to be true. Right? So again, if you see a 1, 1, that's a 1. If you see a 0, 1, that's a 1. If you see a 1, 0, that's a 1. The only time you end up with a 0 is if you have 0, 0. And lastly, of course, not. These are our most basic forms of gates here. And with not, that's a unitary operation, which just means there's one argument, and it just is going to flip every bit. So if you see here, we have the string 1, 0, 0, 0, 0, 1, 0, 1. And we apply a not operation to that. All it did was flip those bits. 1 became 0, 0 became 1. This is something we've already seen, but it's a good refresher because these kind of gates here are very common. All right, quick recall on hexadecimal. So there's our hexadecimal chart. And you can see it goes on what is in binary, what it is in hex, and what it is in decimal. And just as a recall, every 4 binary bits is a single hexadecimal digit. So if you notice, it goes all the way from 0, 0, 0, 0 to 1, 1, 1, 1. Right? Or in hex, 0 to F, or in decimal, 0 to 15. All right, we can't talk about stuff without talking about the ASCII table. Right? And if you look at this ASCII table, this represents 128 different characters. It may not seem like 128, but it's 128. Now, each character is represented with a 2-digit hex code. For example, if I look at it, I see 4F is a capital O. And that's why it goes 0, 0. And if you look, it goes 0 through F, and then the next digit is it's starting at 0, and it's going all the way up to 7. All right, it doesn't go beyond that because this basic ASCII table only has 128 characters. Some other data types, of course, text strings. This is a sequence of characters. It's typically terminated with a null command. Now, typically with this, though, there's not necessarily hardware support for it. This is usually something that's handled via the software language that you're working with. Images, that's just an array of pixels. An array, I'm not going to talk too much about here. That's something more for a programming side again. But what you do need to know is that an image, if you're having a monochrome image, which means that it's black and white, there's 1 bit to represent 1 or black, and 1 bit to represent 0 or white. If you have a color screen, it's typically an RGB components that are 8 bits each, and so that's how you get the different tones going in with the RGB colors. There's other properties that are out there, such as transparency. So if you ever look at, for example, some images like PNGs, and you put them against other images, you'll notice it doesn't have like a white box around it, like some images, like JPEGs do. That is transparency because it takes that area there and it sets a flag for transparency. Hardware support, again, typically done is in general purpose processors. A lot of that is, again, written into like the different pieces of it. There's some stuff with MX, which allows for multiple 8-bit operations on a 32-bit word. If you recall, words versus a sequence of characters. All right, and lastly, of course, sound, which is simply just a sequence of fixed point numbers. This is, of course, a little different from an analog sound, which might be on, like, for example, record. This is digital sound, which comes off of your computer, so like your MP3s are digital sound. All right, the LC3 data types. We will be looking at a special learning device in this chapter, which I've kind of already mentioned, which is the LC3, or the Little Computer 3. The LC3 supports only 16-bit complement signed integers. For logical operations, it's only going to support AND, add, and not, which means I can do an AND operation, I can add binary numbers, or I can do a not operation. Anything other than those three, I have to kind of get creative with how I'm going to approach the problem. So, like, for example, I want to do a subtraction. Well, if you remember your rules of math, if I want to do a subtraction, well, that means I have to add the additive inverse. So it'd be like adding the negative. Again, you'll have to go a little creative if you want to kind of do like an OR operation and stuff like that. But we will look at more with the LC3 next time. Until then, folks, I'll see you later.